direction is this and this. So this kind of this red arrow means this is the orientation of this triangle, and it's the right hand row is pointing outward of the sphere, and so this we claim this one have a positive orientation. But when you have this G0, let me see, this is 0, 1, 2. 0, 1, 2 is here. 0, 1, 2. When you have 0, 1, 2, you can see that for the 0, 1, 2, the dominant direction is this one. So it's pointing inwards towards the inside of a tetrahedron. So this 0, 1, 2, this triangle have a negative orientation. And we should put a star here. But because it's pure Yuan phase, the star and inverse is the same thing, so we just put the inverse. Okay. So that's it. So therefore, the condition that on every sphere, the action amplitude equal to 1 became this condition. So therefore, then things became very simple. Is that to have a non-trivial topological term, we just want to have this. We need this symmetry condition, and we need this condition, and this has called a cohomology condition. Well, it's not. I didn't invent this thing, so mathematicians invent this thing, so they call it somehow called a cohomology condition. So basically, and this nu is pure Yuan phase. So these three conditions together is basically some kind of nonlinear algebraic equation. I will try to find solution of this big set of nonlinear algebraic equation to see whether we have a solution or not. Then the solution of this nonlinear algebraic equation is called the cohomology. The new set of this equation called cohomology. Then for every solution, then we have this looks like we have a non-trivial topological term, and that's it. Yeah.
So for the counter example, if it's not on a sphere, for example, is it on a plane or something? Just to find a counter example.
Okay, and this is a very good question. Let me say the following also. Okay. You can see that even in the field theory, we have this topological term. We say that the integration of topology is always equal to integer, which is not true actually. It's true only if the space-time is a closed manifold. If space-time have boundaries, the integration of this kind of topological term or this kind of topological term is not integer, can be fraction number. So therefore, when the space-time have boundaries, the action amplitude is not equal to 1. So this condition is only for closed space-time, and this is very important. And when the space-time have a boundary, the action amplitude is not equal to 1. So therefore, the different paths do not have a trivial constructive interference, so maybe there's non-trivial dynamics. So that's the reason why the boundary have non-trivial dynamics. But however, if space-time have no boundary, all the paths have action amplitude equal to 1. You have a trivial constructive interference, and seems pretty trivial. And so here we do the similar thing. Is that when we imposing this condition that the action amplitude equal to 1, I should write this down. We require that this condition is only for the space-time with no boundary, for closed space-time. And the simplest closed space-time is a sphere. And in a sphere, there's many different ways to triangulate that. And here we choose just simplest triangulation. There's using 4 triangles to make a sphere. And then we get this condition. Okay. So here we pretend that the new set of this condition gives rise to this topological term, because the action amplitude always equal to 1. And certainly this topological term actually is defined on space-time lattice. So basically we kind of fulfill our purpose that we find some kind of a space-time lattice topological term, just a solution of this kind of a cohomology condition. Okay. But however, these topological terms are not quantized. What I try to say is that many different topological terms can be continuously connected. If 2 topological terms can be continuously connected, we should not say these 2 topological terms describe a different phase. Only topological terms which cannot be continuously connected to each other they may correspond different phase. So here we try to say, in the solution space, what is the connectivity of the solution space? You know, if two solutions can be continuously connected within the solution space, we say they belong to the same phase, they describe the same phase. If they are not connected, they belong to different phase. And to understand the connectivity of the solution space, then we notice this kind of a structure. Suppose mu2 is a solution of the cosine condition. Then we can immediately construct another solution, mu2 tilt, using this formula. And this formula also have some very nice structure. Is that this actual factor, this beta 1 also phase factor. Actual beta 1 actually is defined on the link. Remember mu2 defined on the triangle. Then we can have something defined on the edge. Then modify using multiplication, using this kind of multiplication, we get a new solution. So this beta 1 defined on edge. For example, for this triangle 0, 1, 2, that's a 0, 1, 2, that's a triangle. We have a beta 0, 1. So beta 0, 1 live on this edge. So this is the phase associated with this edge. Beta 1, 2 is associated with this edge. Beta 0, 2 associated with this edge. And also you know which one go upstairs, which one go downstairs. Looks like 0, 1 and 1, 2 are in the same direction. So 0, 1, 1, 2 in the same direction, so they go to upstairs. And 0, 2 is they go to opposite direction, so go to downstairs. Again, they follow this rule that when the edge have an opposite orientation, you get the inverse. And so then so basically this one define a path integral on this small circle. You know, this triangle, 3 edge from a circle. So the path integral on this circle is this. We just put the path integral on the circle here. We're using this path integral on the circle to modify the path integral phase amplitude on the triangle. And using this way, we find this also solution. Why? Because this modification is on the edge. So when you glue this triangle on the together like this, each contribution from the edge appear twice, because this edge appear as edge of this triangle, and this edge also appear as edge of this triangle. They appear twice, and due to their convention, you can see that this beta appear twice, but once above, once below, so they just all cancel each other. So this term is all cancel each other. So this is mu2 also solution. And because beta is an arbitrary phase, so all the mu1, mu2 tilt, and mu2 are connected by smoothly deform beta from some phase to 1, and so they are connected. And then there's a belief, I don't have proof that the connected components always have this relation. So if two solutions are connected, then they are related by this relation. Okay, then this particular combination is called a coboundary actually. And then we say these two, mu tilde 2 and mu2, differ by this phase, differ by coboundary. We say the two cocycle differ by a coboundary that are connected. So therefore, we should view the two cocycle differ by one coboundary as an equivalent. And so we should quotient out of the coboundary. And then the quotient, after we quotient out this coboundary of this pi 0 of this space of solution is this H. That's group cohomology. That's it. That's group cohomology. Okay. So this way we can see that we find it. Yeah, that's the definition of group cohomology. And so we can see that the group homology simply describe a different class of 2-pi topological term. Okay. And okay. So maybe let me just very quickly. So this is some formulation. So the idea is I will already describe all the important idea in one plus one dimension example. But all this picture can be generalized to higher dimension. And it turns out that it's convenient to define a delta map. The delta map basically maps a function with d plus 1 variable to another function called delta nu, which have a d plus 2 variable. So what is this function of d plus 2 variable? So okay, this is the function with d plus 2 variable, so it's from g0 to gd plus 1. And then what we do is that we just say we drop the first variable, then we get the d plus 1 variable. And then using d plus 1 variable plug into this function, that's become the first term in this product. And then we drop the second g1, then using the remaining d plus 1 variable plug into this function, then get the second term in this product, and etc. So then the product of all this gave us a function of a d plus 2 variable. This is called a delta map. And with this delta map, then we can write a cocycle condition very simply. That if this is cocycle, that means its delta map should be always equal to 1. And so this cocycle condition can be written in arbitrary dimension in a very systematic way. And then this coboundary can also be written very easily. That coboundary is delta map of something with a lower dimension. So basically, if two cocycles differ by something of a delta map, then this one is a coboundary, so they differ by a coboundary, so they are equivalent. And so this delta map defines this so-called co-chain complex. And so it's kind of like a derivatives, derivatives. And then that's a defined, that's how mathematicians view the group cohomology. Okay, so in this way we can obtain the group cohomology in any dimension. Okay, so let's explore some kind of property of this fixed point action. Remember that let's go back to 1 plus 1 dimension. Remember we pick the action. Picking action means we're picking this function. We pick a function, we define our path integral. But our action satisfies this condition. Okay. Then here I want to say that the new satisfies this condition actually define the RG fixed point. And so why is define RG fixed point? Because if nu satisfies this condition, we find that the path integral are triangulation independent. Say we have a region, we can triangulate in all different ways. Okay. And but we can also change triangulation by doing this. So that's another triangulation. So there's an issue that when you have manifold, when you put different triangulation on the same manifold, whether the path integral is same or not. In general, they are not the same, because for every triangle we have amplitude, and when you choose different triangulation, you have different amplitude. But however, for this particular choice for action amplitude, we find the path integral defined for this kind of new tool are triangulation independent. To see this, let's look at this. For example, we have this square. Okay, this square have two different triangulation. Either can be viewed as these two triangles, can be viewed as these two triangles. If you view this square as these two triangles, then the contribution from this square is a product of these two. When you view it as these two triangles, then the contribution from these two different triangles is different. It's these two. But however, we find that these two contributions are actually the same, because if this condition is satisfied, because if you move this to the other side, this equation, is the same thing. Okay, so that means we can modify the triangulation without modify the action amplitude. We can do something even further. That's we can have a 3 triangle with one vertex here. I can remove this vertex to make it one triangle. So that's also change of triangulation. And you can see that for 3 triangle, we have a contribution of 3 amplitude, and for one triangle, we have this 1 amplitude. And then we can move this to the other side. Again, this is same as this. And that's it. So that is the triangulation independent. So basically, when you have a space-time, usually to describe a path integral in the space-time, we need to choose a very refined triangulation, because this triangulation is like a cutoff scale. So usually in the continuum limit, we should take in the thermodynamic limit, the cutoff scale should be very small. We should choose very small cutoff scale. But however, but for this kind of action amplitude, even we have very fine triangulation, we can use in this kind of a move and this kind of move, and to reduce number of triangle. For the sphere, we can reduce at the end reduce to only 4 triangles. That's the minimum number of triangles to make a sphere. So therefore, this kind of path integral, we can evaluate this path integral for arbitrary space-time exactly, because for every triangulation, we can reduce them using this rule to find the number of triangles, then just sum them over. Okay. So that's a standard picture that the RG fixed point is the path integral independent of triangulation, independent how fine you triangulate space-time. So therefore, this is really not very nice. This is RG fixed point. And actually, that's kind of consistent with our picture that this kind of a theory is really RG fixed point theory. And then the mathematician also asked another question, which is also very important question, is that so here we say that on the sphere, the action amplitude equal to 1. So this is a sphere, but this sphere, so this sphere only have a 4 triangle, but here, because this is invariance, you say that even when you triangle the sphere with many triangles, the action amplitude is still equal to 1. But then there's another issue, is that how about if space-time is a torus? If space-time is torus, what is action amplitude? Is that equal to 1 or not? And this is related to the topological invariance. Remember, the mathematician try to want to classify space topology using this function, this function, and this new to actually define this kind of topological invariance, because the evaluation of this partition function is independent of triangulation. So maybe only depend on topology. And so maybe for sphere, this is equal to 1. For torus, this is not equal to 1, some other value. Then this cocycle can be viewed as a way to construct topological invariance, which classify 2-dimensional manifold. That would be really nice. Okay, but however, for this case, we can show that the partition function, maybe action amplitude. Maybe let me write this way. The action amplitude for the torus actually still equal to 1. Why? Because we can view torus as a gluing of a 3-sphere. Okay, maybe let me draw this way. Okay, so here we have a 3-sphere. Okay, so you can imagine if you glue 3 spheres together, so this 3 spheres touch at some finite area. They touch at the finite area, not touch at one point. Then if you remove this touching area, then we get a torus. Okay, and but however, for this touching area, it's actually double layer. You know, one triangle, suppose touching area is a triangle. One triangle belongs to this sphere, another triangle belongs to this sphere. But however, remember each triangle is a pure U1 face. And these 2 triangles actually have an opposite orientation relative to this sphere and this sphere. So these 2 U1 faces actually cancel each other. When you glue these 2 spheres, the contribution from this overlapping triangle cancel each other. So actually, the action amplitude is a 3-sphere corresponding amplitude of this torus without removing this overlapping half. So from here we can show that for any space-time manifold, if this manifold can be constructed by gluing sphere together like this, then the action amplitude is still equal to 1 because they still coming from this action amplitude of sphere. Yes.
Actually, sphere and the torus have very different Euler numbers. Are you saying that they have the same triangulation?
No, they are not. The thing that when you glue them together,
seems you are saying that torus and a three sphere have the same triangulation, but that's
not quite. I think there was a double counting. We double count this this overlapping part is double counted. So, and then because this double counted triangle, because their contribution happen to cancel, so we can really remove this.
But then they just correspond to something that goes around one of the necks in the torus.
Yeah.
Right? So in the torus, I can simultaneously have path.
So basically, what I try to say is that we really have a action amplitude for this three sphere.
yeah.
But however, there's three region. There's a double counted triangle, and because these two triangles enter with different orientation relative to this different sphere, the action amplitude happen to have opposite U1 phase. They cancel each other. So so therefore we can, because they cancel each other, we can really remove this three part. When we remove these three parts, the whole thing became like a torus.
Okay.
And so here I cannot claim that the action amplitude on every space-time topology equal to 1. But at least on those space-time topology which can be glued using the sphere, they equal to 1.
What about RP2?
RP2 is not orientable. So this is very crucial. Everything here, we only space-time must be orientable. If the space-time is not orientable, everything fails. So this one do not apply to non-orientable space-time.
You have three spheres. Do you mean that you have three copies of the system?
No. We just have one system define a space-time with the space-time is a three sphere. Which also same action amplitude. For it can view as because they're disconnected, so it can view as a stacking of three systems as also fine. But we don't view this way because we when we this is very important is that here is before we do path integral because the G the G element on each vertex already is still fixed. We don't do any sum. So before we do the sum, we can do this. So therefore, that's action amplitude for the particular path. Okay, and so this point may be important because so in higher dimension we have a similar thing. In higher dimension, on the higher dimensional space-time manifold, if this manifold can be constructed by gluing spheres, then we know their action amplitude equal to 1. However, if I don't know whether in higher dimension, in 2 dimension, all the 2-dimensional closed manifold can be obtained by gluing sphere. So therefore, they're all equal to 1. But in 3-dimensional, 4-dimension, I'm not so sure. In higher dimension, whether every closed space-time manifold can be obtained by gluing sphere or not, I don't know. And if not, then there will be issue for those manifolds which not coming from gluing sphere. Whether group cohomology action amplitude is equal to 1 or not, we don't know. And this is crucial because we try to say that the group cohomology describes trivial topology order, so that the action amplitude do not depend on the topological space. Is inconsistent. Is consistent with our desire that this kind of formulation describes trivial topology order. So they do not depend on space-time topology. It's just all trivial. And so this is this is our understanding. So we wish we can understand better. Say what is a partition function for space-time manifold with some arbitrary topology? Whether those arbitrary topology can all be constructed by gluing sphere or not? This kind of beyond me. But there is so-called handled body construction of a topology space, and whether from that point of view, whether we can get something, I don't think. But those are basically the standard topic of algebraic topology. So you can see that this kind of algebraic topology issue would naturally enter into the physics in this way.
Why is the orientation important? Why cannot you use like the Klein model?
And the orientation corresponds to the reversing the time.
Oh.
So here, we do not assume our action have a time reversal symmetry. And so so therefore, so we only consider orientable space-time manifold. If you want to consider space-time with time reversal, an orientable space-time manifold, that corresponds to the system with a time reversal symmetry. And so here we don't discuss time reversal symmetry. Okay. And so maybe in the remaining few minutes, so let's show. Now here I already touched the issue. We try to say that the partition function on any space-time topology is equal to 1. So that's suggesting it's a trivial topology order. And here I want to show that it's indeed have a trivial topology more explicitly. You know why the system defined this way describe a system with a trivial topology order, not system with non-trivial topology order. But first, I want to say that once we define the path integral, you know, NTU-2 define the path integral, we naturally define the ground state wave function. And the way to define ground state wave function is like a big bang theory, not a soap opera. Is that so we have a big bang at the space-time origin, so this is the big bang point. Then the time direction is the circle, you know. And then as time evolves, then we just go into circle. Then when you evolve the present time, we have this boundary is a present time. Okay. And because we are doing the imaginary time path integral, so we can imagine that we have a very long time evolution. So after a long time evolution, all left on the boundary is a ground states. Because non-ground state all at exponential decay to 0. Only left is ground state. So therefore, when you do this path integral, summing over all different paths in the middle, fixing the index on the boundary, then this function depends on the boundary index naturally is a ground state wave function, and that's it. Okay. And then we can use in the triangulation invariance is that actually, when you have a long time evolution means we have many triangles here. But because we have fixed point action, so we can reduce many triangles into the minimal number of triangles. So this is a wonderful minimal number of triangles, not quite minimal yet. But I think we can reduce this canonical form. So therefore, by summing over these few triangles, we actually get a ground state wave function. So therefore, we can write down the ground state wave function explicitly for our fixed point theory, and that's it. So once you know NTU, we know the ground state wave function. So that's the ground state wave function. And then after you obtain the ground state wave function, we need to show that this ground state wave function do not break symmetry. Y is symmetric. And the symmetric really means that maybe it's here. It's a symmetric because so this picture shows it's symmetric. So clearly we show that so symmetric means this ground wave function should be equal to, it's a symmetry transformed ground wave function should be equal to this. Because a symmetry transformation means we multiply G to every variable. So that's it on the boundary. And so this should equal to this. Why so? Because of following. And so we can multiply G to every element. So this equal to this. And this is using the symmetry property of this nu, because if you multiply G to every variable, nu is invariant. That's symmetry property for NTU-2. So from here to here, we use a symmetry property. And from here to here, we use a triangulation invariance. Why? Because now this internal variable is a G times G star. Okay, but we can using triangulation to remove this point. We can actually remove this point. And then we insert this point back, but with a G star. And that's it. And so therefore, so this equal to this. So then that's a ground state wave function is automatically symmetric and a G transformation. And this ground state wave function also local unitary equivalent to product states. So here let's consider a particular product state, which is on every lattice point, we have a superposition of these states, which is labeled by group element. Okay. So if I write down the wave function, this particular wave function basically is a constant wave function. So that's for every choice of index, wave function